start.
Yeah.
Welcome, internet. What's up, Suna?
I was waving some Tuesday.
Wait, what? I didn't hear you.
A Ziploc bags?
I still didn't hear you. Wait, crap. Where's my thing?
She said a box of Ziploc bags.
Yup. I had a. Oh, there it is. Over there. Okay. Welcome, internet. Other people in discrete math, presumably, possibly other people in the world watching this lecture. Yeah, it is thrilling. What I'm going to do right now, Yoni, is I'm going to prove this theorem which I mentioned at the end of last class, and you can help. It says, it is a sufficient condition for the existence of a Hamiltonian cycle. Who's pumped? You, pumped? All right, good. Okay, so here is the theorem. The theorem says, and this is gonna take like 20 minutes, it's gonna flip over. It's really awesome. I think this is the hardest proof that we do all year. Theorem. Let G be a simple graph with n greater than or equal to 3 vertices. Here's the, and also, let delta be the minimum degree of the vertices. And the theorem says, if delta is greater than or equal to n over 2, then G has a Hamiltonian cycle. Okay, let's take a second to process this. We have a graph. The graph is simple. It has n greater than or equal to 3 vertices, and this says, this notation is kind of weird, but it says take all the vertices and let's take the vertex with minimum degree, call that delta. If delta is greater than or equal to n over 2, then G has a Hamiltonian cycle. Okay, so the idea, we talked about this at the end of last class. The idea is you want a Hamiltonian cycle. What is a Hamiltonian cycle? Let's do class participation. Lyndon, what's a Hamiltonian cycle?
It's a cycle that contains every vertex.
It is a cycle which contains a vertex. Hamiltonian, it's like whatever. Some people, I feel like Hamiltonian sounds better. It is a cycle which contains every vertex. So you start with a particular vertex, you go all the way around, you touch every vertex exactly once, and also, it's being a cycle, which I believe a cycle, it's all blending together, but a cycle is like a closed, it starts where it ends. You have to start back where you started, yeah. So basically, this is what I was like kind of mumbling and rambling this last class as the period ended, which is you have a bunch of friends, and they have a bunch of friendships, or you have a bunch of people, some of which are friends with each other, and it's a mutual relationship. And let's suppose that the friendship looks like this. Does there exist a Hamiltonian cycle in this kind of friendship graph? Eob says no. I say no also. Can you think of a particular person who could start and tell a secret to another friend such that the secret would eventually come back to them?
No.
No. How about now?
Nope.
Still no, right? Intuitively, this guy is not friends with enough people. How about now?
Yeah.
Now, yes, I think.
Yeah.
I think. Where do we begin?
No, you can't.
Down the bottom. Yeah.
Still not?
No, no,
Yeah,
Oh, you
yeah,
have to
start-
visit
no.
each vertex once.
Start on the bright one. So right
This
above.
over here?
Yeah.
Okay. And then go.
Oh no.
No, you can't.
No, you have to
No,
start with
it's
the guy with 3.
But you have a.
What's up?
Oh yeah.
Don't you have to start with the guy with 3?
I don't know.
Someone has 4.
Yeah. Well, no one has 3 actually.
Start with the guy with 4.
Oh yeah.
Well, start with the guy with the most and then...
Start with the guy with the most and then take it from there.
Yeah.
So if I go zum, but I have to end up back with him. He's too popular.
But can you end up back and then just
Sorry.
keep
No,
going?
No, you have to
Start
hit
with
each
the
vertex
right
only
one,
once.
exactly There's no Hamilton.
Yeah.
Yeah, I think there's not one. So should we add one more?
No, wait.
Oh, no, there is.
Okay, well, even if there was, who cares? Doesn't matter. Now is there.
probably.
Now there should be. You can just do the star, right?
Yeah.
Yeah. So if I start with here, I do this guy first. Then I go here. So 1 has a secret. He tells the secret to his friend 2. 2 tells the secret to his friend 3. 3 tells the secret to his friend 4. Wait, I screwed up.
It should be 1 across to 2.
This is embarrassing. But anyway, I don't feel like doing this. Example abandoned. But basically, if it is possible for one person to tell a secret and for it to go all the way around and then get back to them, then that's a Hamiltonian cycle. Cool, say cool. Okay, good. Okay, so what this theorem says is that if everyone has enough friends, then it is possible to do this. And enough is, you have to be friends with greater than or equal to the number of people. So if there are like 11 people in the room, then you have to be, every single person needs to be friends with at least 6 of them, right? Say right. Yeah, so everyone is friends with half of the room or more, or slightly more. Okay, good. If that is true, yeah, you used this theorem in the homework, but you didn't prove it. The proof's really hard. I'm going to do it right now. All right, and before we start the proof, note that one thing has not been mentioned, which is that the graph is connected. Okay, well, you pretty damn well better be connected if you are going to have a Hamiltonian cycle, because you need to get all around, right? But so step 1, I will show that indeed this implies that it is connected. This. Okay, so note, if G has a Hamiltonian cycle, if G has a Hamiltonian cycle, G must be connected, duh. And so now comes my claim. If delta is greater than or equal to n over 2, in other words, if everyone has enough friends, then G is indeed connected. Then G is connected. Okay, why is this true? All right, well, I think the thing to do is to do a proof by contradiction. So suppose not. And by suppose not, I mean suppose not connected. And I'm going to hope to arrive at a contradiction. So basically, does everyone see what I'm doing? I'm showing that everyone being friends with at least half of the people implies that the graph must be connected. And basically, if the graph is not connected, then you must have some components. This is similar to a proof we did last class. So I'll just write, then there are at least 2 components. There are at least 2 components. Let's call those components C1 and C2. Okay. And let's let the size of component C1 be N1, and let the size of component C2 be N2. Okay, well, if you add up all the vertices by the size I mean the number of vertices, right? So let N1 be the number of vertices in the first component, let N2 be the number of vertices in the second component. So either there are 2 components or more, right? If there are only 2 components, then when you add up N1 and N2, you're going to get N. If there are more than 2 components, anyone, forget about oh, you're looking at the proof? Okay. What are you doing over there? Mr. Rose, please look away. Don't talk. Okay, good. If there are more than 2 components, then when you add these up, you're going to get something less than N. Okay, so claim N1 plus N2 is less than or equal to N. Everyone agree?
Yes.
Okay, good. Let me see this. All right. So, many more space for this. Take a vertex which is in component 1. Okay, so I decided I need more board space. Is the camera on me? I think it is. So here's component 1. Here's component 2. Take a vertex which is sitting over here in component 1. So let's call that vertex V1. Well, just like recall, are both in frame?
Yeah.
Okay, good. Okay, recall that n is greater than or equal to 3.
Why is it? It's not budging.
What's wrong? Sorry.
Nothing.
It's fine, good, okay. N is greater than or equal to 3. So if n is greater than or equal to 3, that means how many friends does V1 have? At least 2, right? At least 2 friends. because, so I'll just say, since n is greater than 1, by our assumption, C1 is the degree of vertex 1 has to be greater than or equal to 3/2, because that was our theorem, right? That the minimum degree vertex, the minimum vertex, or the minimum degree vertex is itself bigger than or equal to half of the number of vertices. So since there are greater than 3 vertices, each one. Okay, so there's no one who's just like friends with no one. So the degree of V1 has to be greater than or equal to 2. Or I'll just say greater than 1. And then that holds for the degree of V2 also, where V2 is some vertex in component 2. Okay, cool. So keeping that in mind, I can kind of think about what this sort of picture looks like, right? V1 is going to be friends, there's going to be some sort of situation going on here in this component 1. And there's some situation going on here in this component 2. This is just a very light sketch of the general idea, which is that there's this component where there are some friendships, and there's this component where there's some friendships. Okay, but we have kind of like a problem, right? Because V1 has to have an edge with greater than or equal to n over 2 other vertices. I'll write that down. V1 has an edge with greater than or equal to n over 2 other vertices.
No, it was 7.
But also, what's up?
So like,
In this case, it's 7. But like, let's just kind of
we know that
let's
it's
just
6,
keep this
right?
like let's just keep this picture kind of like just vague. The particular picture is not important. I'm just drawing just a general cloud of vertices that are
We
floating
still have
around
a
here.
minimum of 6, right?
Okay, but no, just forget about 7. Just more dots elsewhere, like just vague. There's a component and there's like another component.
Yeah, but if V1 is connected to 2 things, and like V2 is connected to 2 things, then we have a minimum of 6 vertices now, right? Total.
Okay, I'm just going to ignore you because you're missing the point. This picture's not important. I'm tempted to erase the entire picture. 'Cause
No,
you're
but like
focusing on
that's true
figures.
whether or not you have the picture, isn't it?
No.
Didn't you just say that the degree of V1 is greater than 1 and the degree of V2 is greater than 1?
Yes.
And that they're in separate components?
Yes.
So V1 is connected to 2 things and V2 is connected to 2 things. And
Why is V1 connected to 2 things?
Because the degree is greater than 1.
Could be more than that, right? It's at,
Could be.
there's at least.
Yeah, at least
yeah.
2 things.
True.
At least
Yeah, that's true. Okay. Okay, so you're saying good things. I shouldn't be blowing you off. Yeah, she's saying that since the overall graph has degree 3, has more than 3 vertices,
Yeah.
then or 3 or greater vertices, then as we just mentioned, the degree of V1 has to have more than 1.5 friends, which means it has like 2 friends at least. So if V1 has 2 friends, V1 must be related to at least 2 people, but so must V2 be related to at least 2 people.
And
So there have to be at least 3 people here, and there have to be at least 3 people here, something like that. Yep, good. Okay, but more to the point, if we think about how many vertices are there in component 1? Well, V1 has an edge with n over 2 other vertices at least. Okay, so what can I say about n1? n1 must be bigger than, how many vertices can I know are in the first component?
3.
Wait, no, like in terms of n. Right? So this overall graph has n vertices, right? So that means by our assumption V1 is friends with n over 2 of them or more. So n over 2 plus 1. Right? If V1 is indeed friends with greater than or equal to n over 2 other people, he's only friends with people in his own component. Right? So he's friends with n over 2 other people or more, but he can't be friends with everyone in the component because he can't be friends with himself, right?
Yeah.
So even if V1 was friends with every single other person in the component, there would have to be that many people plus 1, including himself. You guys follow this? It's like a little subtle and like a little bit annoying, but I think it's okay, cool. So, and similarly, the size of the second component, V2 has to be friends with n over 2 people, since every vertex has that property. So there must be that many people in that component plus 1. But what happens when I add up these two inequalities?
You get greater than n.
Yeah, I get that n1 plus n2 is greater than or equal to n plus 2, and that's a contradiction, right? Because the number of vertices in the first component plus the number of vertices in the second component is, can't be more than the total number of vertices, because those are non-overlapping. Who gets it? Okay, I think that was 10% more clear than Constance's explanation. Alright, this was all just to verify some like borderline obvious thing, which is that, the graph is connected. So we haven't even really like started the theorem yet. Started proving it yet. Okay, please perform a rotation of camera and we're going to move to the real business now. Okay, the real business is I'm going to prove that indeed there is this Hamiltonian cycle. The logic here is very complex, in my opinion. Okay, so take some n greater than or equal to 3. So I'm going to prove that this holds for a particular n, and then because n is arbitrary, it'll be true for all n. Alright, let S sub n be the set of all graphs meeting the condition of the theorem, but not having a Hamiltonian cycle. So we would like to show it's empty. Okay. So let S sub n be the set of all graphs such that I guess that the G has n vertices. G has n vertices. Also, the minimum, even the minimum degree vertex is greater than or equal to n over 2, and G has no Hamiltonian cycle. What we are trying to prove is that if the minimum degree vertex is greater than or equal to n over 2, then G must have a Hamiltonian cycle. So the overall structure of our proof is going to be show that this set is empty. Show S sub n is empty is going to be my strategy. Okay. And if this is true for a particular n, then it's true for all n. Okay. Well, so this whole thing's a proof of contradiction. So we're in the absurd world, so everything's a little bit weird. So I'm going to keep talking about these graphs, but our goal is to show that there can be no such graph. Okay. So now, the more friendships that exist between vertices, the greater the chance that there's a Hamiltonian cycle, right?
Yeah.
Okay, so these are all the graphs which have no Hamiltonian cycle. So does everyone feel that if I keep adding edges and keep adding edges and keep adding edges, eventually, suddenly there's going to be one? Okay? So among the graphs with no Hamiltonian cycle, meaning the condition, choose the one with maximum number of edges. I don't see why not. Because this is like a finite set, right? So I think it's fine. Yeah? There can't be an infinite. There's an upper bound on the number of possible edges. It's a finite set, so we're good. Okay, for a particular n. Right? For any particular n, it's a good question she's asking. For any particular n, there's a finite number of possible different graphs, although you and Ethan said like it's like a really huge, ridiculous number. It's in fact 2 to the, how is it again? 2 to the n choose 2. 2 to the n choose 2. Okay, but there's still a finite number of them. So, okay, so choose the graph in S sub n with the most edges. And if there are 2 with the most edges, then just like pick one, it doesn't matter what. And call it G. Okay. Alright, so this was all just the setup. Let's recap where we are. What is going on with this graph G? Well, G is some graph. It is an ordered triple of of vertices, edges, and then there's that like annoying like phi function or whatever that, no, what's that called? Whatever that Greek letter is. Okay, so here's what we know about G. G has n vertices, and each vertex, what's up? What's the null set? No, it's like a, who cares? We don't even need that. Let's go. Because it's a simple graph, so who cares? So it's just a set of vertices and edges. G has n vertices, each vertex with a degree greater than or equal to n over 2. What else do I know about this graph G? Tell me more things. Yeah, thank you. Also, G has no Hamiltonian cycle, by assumption.
It's connected.
It's connected. I don't feel like writing that, but okay, no, actually, I can write that. Actually, I did want to write that. Also, G is connected. Okay, so here's what I know about this graph. It has n vertices. Every vertex has degree greater than or equal to n over 2. It has no Hamiltonian cycle. It's connected. And the last thing, please make reference to its maximality. It has more edges than any other graph in that set. But a more chill way of writing that is to say,
If there's another graph that has, like, that satisfies all the properties, then it has less edges.
yeah, so it has no Hamiltonian cycle, but
If you add any other edge, it will.
if you add any other edges, it will, right? So the last thing I want to mention about G is also, if any graph with more edges must have a Hamiltonian cycle.
Is it possible to just add like an extraneous?
Okay, watch. Just no, wait, hold on. Also, any graph with more edges, has a Hamiltonian cycle. Okay. So that's what this graph is. N vertices. Each vertex has a sufficiently large degree, friends with half the people. There's no Hamiltonian cycle. It's connected. If you add even one more edge, then the graph must have a Hamiltonian cycle. Who's with me? Okay. So from this whole thing, I expect to get a contradiction. All right. Well, let's begin. First of all, could the graph be complete? Say no. Of course not. Because like if G is complete,
Then it has a
if G is complete, then just like that just means every vertex is friends with every other vertex, and there's surely a Hamiltonian cycle. Just go all around. So if G is complete, then of course, there's a Hamiltonian cycle. So G is not complete. Okay. And if it's not complete, then there must be two people who are not friends. So take two vertices which do not have an edge between them. So take two people who are not friends. There must be some. Take two vertices that are not connected. Or I shouldn't say connected. That are not sharing an edge. Adjacent is the word, yeah. I'm teaching this class, I should probably know that word. Yeah, take two vertices that are not adjacent. Two people who are not friends. Okay. Call them W1 and Wn. Call them W1 and Wn. Okay, this is cool. No, N. Okay. All right. Well, here is the idea. There are a whole bunch of vertices out there. These two are not connected, right? These two are not adjacent, okay? And if I add even one more edge, then there will be a Hamiltonian cycle. Okay, so add that edge. Make a new graph by adding that edge. Make a new graph by adding that edge.
It's not a multi-graph, it's a simple graph. So
Yeah,
you
this is a
know
simple
that
graph. Okay, and what happens, so we can call this new graph G prime. So call this new graph G prime. And basically, what is G prime? G prime is just like G, but with the W1, Wn edge. Is that good enough? I could go, that's enough, that's sufficient detail. Okay, what then is surely true about the G prime graph? It has a Hamiltonian cycle, says Lyndon. Yeah, so because, right? So G prime has a Hamiltonian cycle. Because we already said that G had the most number of edges it could have without having a Hamiltonian cycle. So then G prime does. Okay. And by the way, what else can we say about that Hamiltonian cycle? It contains that edge, right? G has a Hamiltonian cycle, and, says Gabe, the Hamiltonian cycle through G prime must contain edge W1, Wn. Because if it didn't contain W1, Wn, then G would have a Hamiltonian cycle, but on our assumption G does not. Is this clear? It's pretty hard. Okay. All this is still set up. Okay. Therefore, and I'm not sure if Yoni's head is in the way or not, we can say that there is a Hamiltonian cycle in G prime. And the Hamiltonian cycle in G prime must, generally speaking, look like this. It involves vertices. It touches every vertex once. The Hamiltonian cycle does not go through W1 and Wn, right? And the whole thing about a Hamiltonian cycle is you're just taking a path through all the vertices. So you can rotate it and begin wherever you want, right?
Wait, it has to contain the path between W1.
It contains W1. Oh no, sorry. It must. It must contain W1, Wn. That's what I meant to say. Yeah. So yeah. So the Hamiltonian cycle in G prime, since it contains the edge W1, Wn, can be written as W1, W2, all the way up to Wn minus 1, Wn, and then back then to W1. I don't know what the notation is for this, so I'll just write it like that. Yeah, that seems good. Yeah, right? Because that's what a Hamiltonian cycle is. A Hamiltonian cycle is a cycle through a whole bunch of edges, which you start at a particular vertex and you end back at the same vertex. And notice how I'm choosing to start at W1 because it doesn't matter where I start, and I'm going to go through the thing. Cool? Okay. So, somehow, by the way, this is going to yield a contradiction. Okay, now comes a giant picture, which starts getting kind of cool. Okay, so here is the pictorial representation of what's going on. Here is W1, here's W2, W3, etc. W4, we're going to just draw a couple more of these. And then we get to ... and now I'm going to call this WK, and this is WK plus 1, and there's an arrow, and then ... and then eventually we get, ran out of room, WN. Okay, so is everyone clear? This is a picture. What is this a picture of? Josephine. The Hamiltonian cycle in G prime. Yep. So there's a Hamiltonian cycle in G prime that starts at W1. So this is the start. Then we go to W2. Okay. So good. So far this is all gossip. Okay. Now I'm gonna Rosify the proof by just making it full of a bunch of stupid shit. Ready? Okay, Yoni. Here's what's happening. W1 is going to tell a secret. Okay? So W1 is the confessor. W1 tells a secret. And duh, you only tell secrets to your friends. So W1 tells W2 her secret. Then W2 and says, please don't tell anyone else. Well, what happens when you tell a secret to someone? They tell other people. So then W2 tells one of her friends the secret about W1. Her friend is W3. Now W3 knows the secret. Okay? And by the way, what do you do when you tell someone a secret that you're not supposed to tell?
Don't tell anyone.
You tell them, don't tell anyone else. In particular, you say, don't tell W1 that I told you.
Yeah.
Okay, so imagine what's happening here, right? W1 has a secret. W1 tells W2. W2 is like, this secret is so hot, I have to tell someone. W2 tells W3. While telling W3, W2 says, don't tell anyone else, and especially don't tell W1 that I told you. Follow? Okay, then W3, by the way, you only tell secrets to your friends, even if they're not about you. So these are all friends, assuming that these are all friendship relations. They're all edges between all these relations. Okay, W3 tells W4, here's the secret about W1, don't tell anyone else, don't tell W1 I told you. Okay, now, there is a well-known snitch in this friendship community, and this is the snitch. The snitch is WN. Okay, so WN is the kind of moral person who, having heard a secret rumor going around regarding W1, is going to tell W1 that he heard this secret. Let's just do all female. Did I already tell you guys about the picture about the old ladies and the thingy last
We
class?
looked
Did
it up
I make
last
that the
class.
headline graphic? Or no?
But Andy and I looked it up last class.
Yeah, there's this,
And it's kind of funny.
it's kind of funny.
Wait.
What?
Which thing?
I thought I was gonna make it the headline graphic, but I think I forgot to. I did? Okay, should we take a 1 minute break and look at the picture?
Yeah.
Okay, let's take a 1 minute break, and, anyone, can you hit stop on the camera?
Bye-bye.
And